It's a pleasure to be here. I feel a little bit of sneaking in here because, in fact, my sort of core activity is looking at past climate change, modelling past climate change, and not always, and that's not just only from volcanoes. And you'll see also that I shouldn't really be here because it turns out that to be a climate modeler of volcanoes, particularly in terms of the past, your surname has to be Jones. We'll see in a minute that Jones is very common throughout a lot of these things, although not the same Jones. It's going to be a double act. I decided that I'm going to do a bit of a review in about 10 or 15 minutes, and then Peter is going to show some very latest results from one of the state-of-the-art climate models that Peter and Jessy are working on. So I'm going to very quickly consider sort of four, in essence, sort of case studies where we're using, in many senses, we're using volcanoes as a test bed to see, do climate models work? You know, volcanoes are a fascinating challenge to model, but they also are a unique test where we can look at fairly rapid change of climate. Can the climate models represent the changes very effectively? And so we're going to say a few words about the challenges of so-called warm winters. We're going to talk about particularly past climate responses, particularly over the last millennium. I'll touch upon super eruptions because well, it's a bit like David was saying, and they get lots of publicity and all that sort of thing. And I want to also say a few words very briefly about biogeochemical responses. Just to remind you, for those of you who don't know about computer climate models, the idea behind a computer climate model is that we're trying to represent the physics of the climate system. These are models which are not based on, if you like, sort of calibrations or empirical studies. These are very much starting from the basic laws of physics. So we put into them things like Newton's laws of motion and the like. But the trouble is that when you apply it to such a complex domain like the climate system, you have to make lots of approximations. And it's those approximations which is why your climate models are not, you can't just say, oh yes, I believe in the results sort of thing, that you've got to test them, you've got to evaluate them in a rigorous sort of sense. And so as I say, the volcanoes do provide an interesting aspect of that. So there's a number of sort of issues that I'll go over. And the first one I want to think about is think about the whole issue of representing stratospheric aerosols in climate models, and then we'll move on to, as I say, some other aspects of the problem. Aerosols are one of the more challenging aspects in terms of representing them in climate models. There's a lot of both direct physical responses of the climate system in terms of the impact that the aerosols have in terms of both the absorbed solar radiation and also, for that matter, in terms of the emitted long wave or infrared radiation, and so there's some very direct effects on that. There are indirect effects, for instance, in terms of impacting on clouds in the models. Aerosols play a very important role in terms of cloud condensation nuclei, and so potentially there are impacts in terms of cloud cover. And then the other thing which this diagram doesn't particularly show so much is that aerosols and chemistry are can be potentially very important and impact on things like the ozone concentration. So it is a challenge to represent all of that within the computer climate models. And one of the most interesting tests, I guess, in recent years has been particularly focusing on Mount Pinatubo, where we've got a lot of observations, if you like, for certainly the input of aerosols from that volcano. And so, you know, the Mount Pinatubo turns out to be a very sort of vigorous, very active area of research in terms of the modeling of volcanic climate interactions. These are now, I should say, are observations. You can barely see that, but this is showing you the stratospheric temperatures, and you can see that this is the Mount Pinatubo peak. You certainly can't see that. I can't see that from here, 1991. And with a very strong warming, a strong cooling. Well, I say a strong cooling, a cooling of the order note of a few tenths of a degree centigrade in terms of the surface temperatures, and also some very complicated structure of temperature change if you look seasonally. And this showing you the winter, or December, January, February, be more precise, temperature response. So this is showing you the temperature immediately after Mount Pinatubo compared to the decade before Mount Pinatubo. And although a lot of this, you know, what is always difficult when looking at the effects of volcanoes on climate is to know how much of this is a direct response to the volcano and how much is just part of the natural variability of the climate system, because every year the climate is different. But it composites of volcanic climate change following volcanoes very typically shows this pattern, particularly of this warmer regions in the northern hemisphere as a result of volcanoes going off. So although I don't want to put too much emphasis on the really details of this change, the generic pattern of having significant localized warmings in the northern hemisphere is very typical of these types of volcanic eruptions. So can we model those? On the global scale, the simple answer is, I'd argue, is yeah, we're not doing a too bad job. What I'm showing you here is again, it's the same surface temperature and the lower stratospheric temperature immediately after Mount Pinatubo. The black line is the observations, and the grey line here is the simulations. The amplitude is not quite the right magnitude, but there's some hint at least of saying that the pattern of change is sort of comparable. Here, more at stratospheric levels, though, there is more noticeable difference with the black or black solid dots showing you the observations and the circles of the simulation. And you can see that, in fact, the models are actually over emphasizing the stratospheric warming that occurs with that aerosol plume that they're putting in. Part of the reason for that, we think, is that the current, most of the state-of-the-art climate models, or certainly at the turn of the century, did not include any changes in ozone chemistry that went along with that. What you can see here is a result that if you decrease the ozone that we know follows that eruption, you can get a cooling of about 1 degree, and so that does bring down. So that's what the ozone alone does, and that would bring down the cooling a little bit. But it doesn't hint at the fact that the models, in that sense, are actually, if anything, overestimating the change in the stratospheric. Of course, the big debate there is, could that be part of, if you like, the forcing? Is that, are we confident that the aerosol distribution is correct? When it comes to the winter warming that I mentioned, as I say, which is ubiquitous, there are some examples of models. This is a model by Kirchner, the same model by Kirchner. It's the German model, which shows, this is the simulated changes in temperature that from the climate model. This is the observations. Note the first of the Joneses appearing. This is actually Phil Jones from the observational perspective. But what you can see is that, yeah, give or take a bit, there's some hint at saying that the model is getting this pattern of change. What the mechanism is that people talk about, it's very much related to the fact that that we're getting more aerosols in the tropics. That in turn influences the heating and influences the temperature gradient, and influencing the temperature gradient has an impact on the zonal wind strength and the planetary waves at lower levels. So in that sense, that model, that suggests that the models might be doing a good job. However, the very latest results, and this is a lousy picture, I'm afraid. This is actually from a paper that's submitted to, I think it's JGR, which is looking at actually a composite of the winter responses in 9 of the largest eruptions since 1883. Showing you again, it's just the, well, I say the winter, it's December, January, February anomalies. And what you can see, and these are CMIP5, for those of you who don't know, that CMIP5 is basically the climate models, the state-of-the-art climate models that are going into the next IPCC report in terms of future predictions. And what you can see, or at least you can see a huge variety of behavior in terms of the winter warmth. So it remains a challenge to get that winter warmth occurring in the GCM simulations, where some models might be doing it reasonably well. Say this is the Bergen model, but there are other models. Other models show a ubiquitous warming, and other models, the old Hadley Center model, for instance, shows very little change indeed. So that remains a challenge of why the models aren't quite getting that winter warmth. Very quickly, though, so that's one sort of test bed of whether the climate models are working and representing the circulation change. We can also think about the last millennium and the effects of volcanoes on climates in the last millennium. And so again, we've got reconstructions. This is actually Tom Crowley's reconstruction of the volcanic forcing over the last, it's going basically the last 1,000 years. The challenge that we've got there is how believable is that curve? You know, as Steve, in fact, alluded to in his introduction, it's often, a lot of that, the data that goes into that is just from the ice core record. Is that really capturing the strongest volcanic events, and is it really well calibrated in some senses? So that's a sort of big challenge, and then the second challenge is saying, well, to what extent is this influencing this record, which is actually the Northern Hemisphere temperature record from tree rings. And at the moment, there's a huge amount of controversy going on this field. Just in the past few weeks, we've had Michael Mann publish a paper where basically what we're looking at here, this is again effectively the last 1,000 years, or from 1200. There's highlighted a few of the big volcanic events in that record. And what you can see here is that the red curve is showing you what the climate models are showing for global mean temperature change. And the blue curve here is showing you what the proxy data is, the tree ring data for the same period. And what you can see is the fact that the climate models are actually giving a much bigger response of cooling than what the tree rings are doing. So the tree rings might be saying that you're typically getting some of these big volcanoes about 0.5 degree, 1 degree cooling of the climate system, whereas the models are actually going to 2.5 degrees. Now, at first, that looks bad news for the models, but what, in fact, Michael Mann is arguing for in his paper is actually saying it's the tree rings that are wrong, and that basically the trees stop growing when the climate gets cold, and so they're actually sort of capping the change. And so that he argues that, that in fact it's the models that are right, and actually the proxy data that is actually wrong. However, as you can imagine, there are other views to that. And the other view to that is, again, even more recently published, Philip Broha from the Hadley Center. Rather complicated picture. Let me just focus in, say, on this top diagram, where basically he's actually focused, rather than relying on the proxy record, the tree ring record, he's gone back and actually used historical archives to come up with estimates of, instrumental estimates of temperature change from 1790. And so you could look at quite some detail at the 1809 and 1815 eruptions. And the black dots are showing you what the observations suggest to be the temperature change going along through those two, 1809 and 1815. And the other curves are showing you the climate models. So in that case, it seems to be saying the climate models are overdoing the thing, and that actually the observations are okay. And so there's a huge controversy at the moment. A lot of that controversy revolves around saying, you know, is it the climate models are wrong, is it the proxies are wrong, or is it the actual aerosol loading that's wrong? Is it the forcing effectively? And it's that challenge, if you like, that as a climate modeler, I would desperately like to be able to unravel which of those is the case. I'm going to skip over that because I'm conscious of time, and David talked a little bit about that. I just want to say a couple of words about super eruptions, because that's been a very popular area of climate modeling, again, because of popularity. And this is yet another Jones. So previous diagram was Phil Jones. This is Gareth Jones of the Hadley Center, who modelled, for instance, Toba, showing that from a modelling perspective, you can get a huge change of temperature. This is a global mean temperature change of 10 degrees centigrade, lasting, though, only for, or at least the biggest of the changes, lasting for just a couple of decades, really, after the eruption. So it's a very rapid response. In this particular model simulation, it seems to be the larger the model, the larger that you hit the model, the more clearly you do get winter warmth often coming out of it. And so with Toba, it actually does turn out to be quite easy to get winter warmth there. But you can see a very significant changes in temperature. And note, the color gets saturated here, but the sort of numbers that we're talking about is actually regionally a cooling of about 25 degrees centigrade. So phenomenal cooling with that. With the that type of super eruptions. And there's lots of discussions in the literature. David just touched upon it. Blimey, I've got 5 minutes and I want Peter to say a few words as well. But there's lots of discussion about the impacts on human evolution. Very quickly mention another feature of volcanic, large volcanoes that are going off. This is now Morgan Jones. Published a paper. In fact, the coastline's completely lost on this diagram. The North America is here. But basically, cut long story short, he was highlighting the fact that as well as thinking about just the aerosol loading, you've got with some of these super eruptions, you've got a huge covering of ash on the ground, and that changes the surface albedo and can have a really big impact on climate change. Probably in terms of the global scale picture, that's only relevant for the really big super eruptions rather than the smaller ones, but nonetheless, it was a significant change. And the final comment I want to make before handing over to Peter is yet another Jones. This time it's Chris Jones, who's been looking at the biogeochemical effects of an eruption. And basically, this is going back to Mount Pinatubo, but one of the things that we saw after Mount Pinatubo is that the rate of increase of CO2, so it's the anomaly of the rise of CO2, actually dropped off for a few years after Mount Pinatubo going off, and with the newest generations of the models which are representing some of the biogeochemical features, we're beginning to be able to represent that change in the CO2 itself. In this particular model, it's entirely down to the fact that the climate was cooler and that actually favored plant growth, and so the plants absorb more CO2 out of the atmosphere. There was a little bit coming from changes in diffusive radiation. So very quickly, in terms of the summary of what I'm saying, is that basically volcanoes do act as a fantastic natural test of the climate models. And they allow us to really say, do the climate models get the right speed of change and the right magnitude of change? But it does require us to know that forcing very strongly, or very well, if we're going to actually say that the models are wrong. And that's even more true when we look at past changes. And I just touched upon the fact that biogeochemical responses are really very poorly represented at the moment in climate models. But there is just a few minutes more, if we can. I had about 5 minutes left. And so Peter's just going to say a few more words about the very latest work with the very latest generation of climate models, talking about Tambora.
Thanks, Paul. So you've heard a little bit about the Tambora eruption of 1815 in the previous two talks. So this is just a sort of brief overview. So this is a nice picture of Tambora. And this is the ice core record of aerosol loading that we've also heard about with Tambora indicated here. So it's one of the largest eruptions of the last few centuries. We've been using, so one of the sort of latest, most recent developments in climate modeling to simulate this volcanic event. So here I've kind of tried to describe the sort of previous generation of climate models. So they typically include obviously the atmosphere and ocean sea ice, some representation of the land and ocean carbon cycle, as well as obviously some representation of the atmospheric aerosols. The model we're using sort of developed out of that includes a significant number of new interactions between these components. So, for example, the atmospheric chemistry model derives emissions of methane from the terrestrial vegetation. The oxidizing capacity of the atmosphere and the troposphere, affects the aerosol loading, and so on. So this is quite an exciting opportunity to test the, as Paul says, the climate response in climate models given some sort of aerosol forcing. So here we've been using, it's called HADGEM2ES, so it's the latest coupled Earth system model from the Hadley Centre in the UK. We've been performing idealized simulations of the Tambora eruption, basically following the ice core record of sulfate loading in the atmosphere, which is shown here. So this is Crowley et al. 2008. And you can see the Tambora eruption. Oh, sorry. Sure. I can hear that now. Some details about the model are shown at the top. So it includes, as I say, an interactive vegetation scheme, atmospheric chemistry, and ocean carbon cycle. So just some quick summary of the results. In response to this volcanic eruption in the model, we see about a degree of cooling globally. And you can see the pattern of the anomaly and the surface temperature and the precipitation shown in the bottom. So we get strong cooling over land, quite a strong signature over North America, and quite strong changes in the tropical precipitation. In this model, as I say, we can investigate some of the other system feedback. So here I'm just concentrating on the vegetation, so the change in net primary productivity, which are caused by the climatic cooling and changes in precipitation. And you can see there's actually quite strong reductions in NPP, so the primary productivity over the tropics, but also that overall the pattern is quite complicated. And so that's illustrated in this time series here, so showing from just the year before the eruption in the model, we see the time series of NPP for two different types of grasses, which we might use to approximate crops. And you can see for C4 grasses, there's an actual reduction in productivity, whereas in C3 grasses, there's actually an increase after the eruption. And this we can explain by looking at the actual distribution of these two types of grasses in the climate model. So for example, C4 grasses are generally distributed around the tropics, where some of these precipitation shifts really have a strong impact on vegetation. Whereas, for example, the C3 grasses are mostly, in the model anyway, located in Europe, where the productivity seems to respond quite favorably to the changes in climate. We can go a bit further than that and think about, as Paul showed, the change in the global carbon cycle, so thinking about the actual net cumulative impact on, for example, atmospheric CO2. And so in this model, the response is actually fairly similar to the Jones et al. Result, Jones and Cox 2001 used a simpler climate model than the Earth system model we used here. But effectively, we get something like a 10 teragram uptake of gigaton uptake of carbon by the land surface scheme, which corresponds to something like a 3, 4, or 5 parts per million reduction in CO2. You can also see, for example, in this model, the air-to-sea flux in carbon is quite small, so really it's dominated by the terrestrial response. We've heard about winter warming. We looked at this briefly in our model, and we found actually, so these are the, just two examples of ensemble members from our volcanic simulations, and this is the ensemble mean response. We find that actually the winter warming response is very marginal, quite weak, although in some ensemble members there's quite a strong signal. And this is just compared to a different analysis of the climate observations. So we're really underestimating the winter warming, but it'd be interesting to pick apart how different ensemble members behave. Just one slide on the ocean circulation. So ocean circulation is thought to respond quite strongly to volcanic events because of the cooling, especially at high latitudes. One previous study showed quite an increase in the Atlantic meridional overturning circulation. So this is kind of a transport of heat northwards in the Atlantic Ocean, which is thought to really impact on North European climate and North American climate. In these model results, we actually see very small change in the ocean circulation. So the differences between these previous studies and ours are going to be the subject of further work. So I'll stop there as we're out of time. The future work, we're very interested in the winter warming, what causes this under what conditions, but I think that's a very big area of study. The AMOC, so the Atlantic circulation changes that we've seen in previous studies compared to ours are quite interesting and could have quite big impacts on the climate around the Atlantic region. It'd be very interesting to look at the dominant controls on the vegetation oceanic carbon cycle. And one of the features we can in the model that we can now test is how the impact of volcanic dust on the ocean carbon cycle. So that will be a future set of simulations. So I'll leave it there. Thank you.